Hello, so in the last video we looked at how the script works and how we can change these variables here to get the behavior that we want, to get the sort of random generation that we want. Now we're going to talk about the script. It all starts with this grid script here, and the grid script was made by Sebastian Legge and is part of the pathfinding system that we have. And it's really acting as the basis of this game, so I'm extremely grateful to Sebastian Legge for releasing these scripts to us for free. And I quote, "for any use we possibly want." So, wow, that's pretty impressive. So what I've done here is, I've made just one extra variable here, which records all of the nodes that are walkable. If you haven't watched Sebastian Legge's tutorials or my dynamic pathfinding tutorials, or my AI tutorials, what I mean by walkability, let's just turn that off, is all these green nodes. These are nodes that the player can walk around on, and they can't walk there. So if I were to have a player and click there, he just wouldn't even move. Right, and if you had someone walking along here, they couldn't go there. If you had unwalkable nodes in a circle here, and you wanted to go from A to B, they'd have to walk around those nodes. So that's what walkability means, by having a walkable node. So I want to record all of those walkable nodes because it's those nodes, it's that list of nodes that's going. It's actually, I'm not really recording the node. A node and a vector3, they're not the same thing, but a node records a vector3 value. So a node, let's have a look at the node script so you know what I'm banging on about. So this is at the node class, and what we're doing in that grid script is creating a grid of nodes. You see here it's a two-dimensional grid of nodes. And these nodes have a bunch of values, and we can extend these values and give nodes different properties. But so far these are, oh, I don't need that one on water node. That's for later maybe. The reason I had that node is I wanted a way to tell whether or not a node was on water, because we want to have some kind of swimming behavior later on, or like sailing a boat on the water. So even though you can't walk on the water, you can swim on the water. So I haven't really thought about how I do that. That's for later. But for now, just comment it out. For now, this is the Boolean variable walkable, which every node has an information that either you can either walk on them or you can't, and they store that. So what we do when we make the grid, and this is Sebastian Legge's method, is that we go, but I changed it slightly. So we have to do it the way that I did it, otherwise it won't work with this system now. And that is that when you create a new node, you have a new position for it based on this what Sebastian Legge did here, and then and here, and then what you do is to determine whether or not the node is walkable, what you do is you send out a sphere raycast from the position of the node, and the position of the node is stuff like 0.5, 0, 0.5. It's always going to be something 0.5, like it's an exact value every single time. Shall I give you some examples of that, I wonder? Probably the best way is to have a look. Well, all of these are instantiated onto the exact position of a node, and as you can see, it's stuff like 62.50, 3.5, 58.50, 21.5, that sort of thing. So it's an exact amount. You'll never get a whole bunch of floats, and it's going to be a precise number, and that's what makes this grid-based game work. I can say, okay, when your vector3 equals this vector3, then do this. In any other type of game, you cannot do that, because the likelihood that two vector3s are going to equal the same number is close to 0. You have all kinds of crazy floats and rounding differences and rounding errors and all sorts of messy stuff when you don't predetermine the exact position of a vector3. So that's what draws me towards these sort of grid-based games, is that it's much easier to code for so many reasons. You don't have to mess around with complex, imprecise float values. You know exactly where things are at any given time. So basically, you send out a sphere raycast from that point. And then what it checks for, based on the radius that you give it, that determines how big the sphere raycast is going to be. What you do then is you check a particular collider. So in this case, I'm hitting a collider which is on the layer of walkable. And you can see that here. There. So this is the walkable mask, and it goes to the collider which has which is on the layer called ground. And that's here. This is this game object. Let's get out of that. This is this grass game object. It has a mesh collider, and the layer is ground. So basically what happens, well, exactly what happens, is it sends out the sphere raycast, and if it hits that game object with that collider with the layer of ground, then this becomes true. But if it doesn't, then this becomes false. Then what we do is when we create our new node, because remember this is a two-dimensional grid of nodes, this is where we actually create the node and we pass in the world point, which is that precise vector 3 that I showed you before. This is the position it has in the grid, right? And that's based on this for loop, this nested for loop. And then this Boolean variable is what determines whether or not the node will be walkable. Because there should be a constructor in here, right? So the first one is that walkable node. The second one is the exact position, which we're calling world position here, node world position. And then grid X and grid Y is where it is on the grid, on the X of the grid and on the Y of the grid. On the, yes, that was right, X on the grid and the Y of the grid. Okay, so that's what that does. And then I just added this tiny bit of extra code here, which goes into this very grid, and it says, hey, look, if the grid at this index, at this X and Y index, is if the node at this X and Y index is walkable, then I want to add it to this list of walkable vector 3s that I have. I'm not adding the node, I'm adding the node world position. So again, you have a look at the node script, it's this vector 3, which stores where the node is in vector 3 space, in 3D space. So that's all of that. Now, the rest of the code happens here. So we've got our list of walkable nodes. We know what we can place objects onto and what we can't. But I'll just quickly make a note. Sorry, I didn't finish fully explaining this. There is a variable, so I briefly mentioned before, there's a variable where this one here, the node scan radius, determines how large the radius is going to be, how large the sphere is going to be, which scans for this particular collider. Now, I set that to be 0.05, so that's quite small. If you set it to some value like 0.5, then it just doesn't work, because I'll show you. Oh, white is wrong. What the hell? I see what I've done. And let's see if you can see this clearly with all these trees and stuff in the way. Notice how you got grass growing on the riverbank. I'll just hide this in case you can't see it on YouTube, but see, it's saying that this is a walkable node, but if you had a character walking out here, he'd be standing directly above, he'd be standing on a river, he'd be just floating in space. So that's not what we want at all. And what's happened there is that the sphere raycast has done its thing, and it's gone out, and it's gone too far, and it's hit this one. So even though the center of the node is not above this collider, and wouldn't hit that collider if the sphere raycast was about that big, which is all I really care about. I don't care about this area as much. I care about the center of the sphere raycast. If the center of the sphere raycast is on this collider, then good, you can put something there. But if the very edge here, if that is hitting the sphere, I don't want it to be walkable. So that's why I set it to quite a small value. That's why I set it to 0.05. And now it will work a lot better. See, now you don't have that issue of things growing onto the riverbank. And it goes quite neatly. You know, even with these bends and that sort of thing. And you notice that here, it would have been a case of it just not being in the right place. And I like it like that, because otherwise you'd be able to plant a tree there, and the tree would basically be half on the ground and half on the river, which would look stupid. Okay, so that's everything I have to say about the grid and the node script. Let's now look at the random forest script. Okay, so the random forest script has these variables here which determine the grass, flower, tree, and rock density. This is a really useful thing that you can do to floats and I believe other variables as well, integers and stuff, where you can add a range. And this is the first time I've used this, and the results were really exciting. The result of putting a range on something is you get a slider instead of a variable, because I can put anything I want in here. I can put some crazy number, right? So that's why it's just like an open box. But when you put some sort of range on there, you get this restriction. So this can only go from 0 to 1. Which is perfect, because what this is, it becomes a percentage, as I mentioned in the last video. And I'll give you an example of that. So the grass density, so first of all, what we get is we get the total number of positions. And what that is that we find that a list that we talked about before, the walkable vector 3s, so all of the walkable vector 3s. In this case, there are 4,085 walkable vector 3s. But obviously in a different map, that would be a different number. That's just what we're dealing with here. And it finds that number, so dot count. So this is an integer, because it's not going to be, there's going to be a precise amount. There's not going to be sort of a half walkable vector 3. So that gets all of the positions. Then we have another variable called available positions. And at first, that's going to be equal to the total positions, right? So available positions at the beginning, before we do any of this stuff, is going to be 4,085 as well. Then what we do is we have this array of environment objects, this one here. And to that array, I'm adding the different things that you can instantiate at runtime. So we don't have the dead tree yet. Well, we do, but I just haven't loaded that in. So that one's actually blank. There's nothing in that particular index. But it's stuff like the tree, which is actually a basswood tree. That's what it's modeled from. A bulrush, grass, flower, bluebells, and then 3 types of rock. So those are all the prefabs that we're working with so far. Now, once that's finished, there are these 4 methods. So it's really just one method, but these have been extended with different parameters. I've forgotten what the word for that is. That's embarrassing. Well, not really. I think you know by now that I'm not a brilliant programmer. I've just forgotten what it's called when you extend a method with different parameters. Okay, so the first one, what we're doing is this is for environment objects that you can walk over, so grass and flowers. They're not going to stop you from walking. Later on, I suppose what I could do is add movement penalties to those objects. So if you walk through some dense grass, you're going to move slower than if you... Actually, I'm definitely going to do that. But for now, they don't inhibit walking at all. And so all we have to do for these ones, and they only take up 1 unit. They only take up 1 node. They're smaller. So they're not taking up multiple vector 3s at once. And so for those, what we do is first we calculate the veg density. So the veg density is going to be a percentage of the total number of positions. So for here, if we have on the slider 0.25, then it's going to be 4,085 times 0.25. So 4,085 times 0.25, which will give us 1,021.25. But because it's being cast to an integer, so this 1,000, that's going to equal 1021.25. But because it's being converted to an integer, this is what's called truncated. I think that's how you spell it. Truncated. Which means that the decimal is not rounded, it's just being cut off. So even if it was like 1021.9, it wouldn't become 1022. It would just become 1021. So what that's done is that's obviously the higher your density value is, the more of a percentage of the total positions it's going to take up. Then what we do is we check to see if the available positions are greater than 0, because we don't want to be doing stuff if they're not. Although this doesn't really create the behavior that I want. I think it should be on the inside of the for loop, not on the outside. Yeah, almost certainly it should be. But anyway, that's for later experimentation. Then we iterate through the total number of veg density. So this will iterate through that 1021 times. So what it does then is it finds a position. And a position is a random walkable vector 3. So it could be anywhere, right? So basically what I'm doing is I've got this list of walkable vector 3s. And then what it does, it doesn't just go in order, sort of like this one and that one and that one and that one, because that would look really awful. Instead what it does is it goes, okay, here, now there, now there. It's just randomly picking out these walkable vector 3s and placing the object, and it keeps doing that until 1021 objects are placed, or whatever the value of the density ended up being. And then what we do is once we found that position, we instantiate this game object, and the game object is based on this parameter, And as you see here, what we've done, this is for placing vegetation, so it's these guys here are both using this particular method. And what we've done is we've used this game object, and this is the game object stored at index 2, which is the grass. So we've just done that. So that's what that is. That's what we pass into this parameter here. So we have to put the density in there. So we've done that here, grass density. We had to put the game object that we want to instantiate, and that's this one here, which corresponds to this index in this game object in the environment objects array. And then we have to give it a parent to become a child of. If you don't give it a parent, you just get this enormous list, thousands and thousands of game objects just going into your hierarchy here, just filling it up. And that's just, you can't work with that. So you have to make sure that you put it into a neat folder, and that gives you a lot of stuff you can do. As you saw in the last video, if you watched that, because I put everything in a neat folder, I could just grab this folder while the game was running, and it's so quick, I can just quickly show you again if you didn't watch it, and then go like this. And then stop playing, and everything vanishes, but then I can just drag that back in again, and haha, I got my forest. So that's really useful. That's just, you know, obviously this is how you want to work. You don't want to be just instantiating things into the main sort of hierarchy list. It's going to look like crap and be unworkable. So then we give it a parent, and the parent is one of these here. We've got a grass folder, a tree folder, a flower folder, and a rock folder. So obviously in this case we're dealing with grass in this example, so we give it the grass folder. So then we have given it the place to be instantiated, and we've given it the game object we want to be instantiated, and we've given it the position where we want it to be instantiated, and then we've given it its rotation, which is just the rotation that it comes with for now, but we're going to change the rotation next. So this is a really helpful method, and I learned about this while I was making this video. I was trying to make a random rotation and not succeeding, and there's this fantastic method in Unity, which is just quaternion rotation equals random rotation, so it's going to be some random rotation value. But then I wasn't sure if this is like all of the different axes, because I just want it to rotate on Y. I don't want it to rotate on X and Z and that sort of thing. Yeah, but I wonder if that's true. Let's have a look. Well, this is going to be a fun experiment. What happens? I'll do it for all of them. Just get rid of that part and see if we get these crazy rotations as a result. And rocks, then it might actually be good for rocks, because a rock rotating in various ways will make it look like you've got more types of rock in your scene. But it's certainly not good for basically anything else I can think of. Oh, yeah. It looks like it's been hit by a nuclear bomb, which I guess is effective in its own right. Like if you wanted to, if that's what you were going for. If I was going for this sort of look though, I'd probably use physics and colliders and stuff, but this looks like devastation. Okay, good. So that was a good instinct. That was something that we do have to do. But for the rocks, I'm going to leave it there. I'm going to leave that commented out because I think that would further assist the appearance of, you know, more than 6 game objects, which is what's really going on. Let's get rid of that. And then what we do, so we have this rotation value which we set to be a random rotation. But then what I do is I set the rotation on X and rotation on Z to be the same rotation as this game object, which is 0, because I don't want them going in all crazy directions like you saw before. And then we set the value, the rotation of this game object to be this rotation here that we just created. Then we set the parent of this game object, so veg, game object veg.transform.setParent to this, which is going to be, it's going to set the parent to be this grass folder in this case, in this example that we're looking at right now. Finally, what we do is we go into the grid, and we go into the walkable vector 3s, and we remove this position. And that's pretty important, because if you don't do that, you will definitely get objects being instantiated on top of each other. So you have to remove that from the walkable vector 3s, and then what we do is we make the available positions the same things as the now diminished walkable vector 3s.count. So that's it in a nutshell, and all of the other methods follow that same logic, except for the trees and the rocks there's this additional thing we have to take into consideration, which is spacing. Because like we looked at before, if you don't take spacing into account, you're going to run into some... why is it still doing that? Didn't I build it? If you don't take spacing into account, you get some stuff that looks really crap. because even though the tree technically only takes up one node, it has quite a lot of space in its branches. So if you make spacing 1, which basically makes these redundant because everything has a spacing of 1 by default, then it looks awful. Even with just 10%. See, it's just like chock-a-block. It's way too much. And you can't really see what's going on. I mean, that doesn't look so bad because at least there are some gaps. But otherwise, no, that's not the way to go. So, how do we work out the spacing to make sure that trees are not instantiated too close to other trees? What I did for that is I used this sphere raycast again. I'm not sure if it's called sphere raycast, check sphere. But it's basically like a raycast that uses a sphere. I've probably made some people who are knowledgeable about maths quite annoyed because a ray and a sphere are not the same thing, right? Sorry about that, guys. Okay, but this sends out a sphere which checks for certain colliders. And that's what I do. So I create this Boolean variable, object in range. And so this will become true if it hits this. So basically the spacing variable determines, exactly like before, exactly like we saw in the grid script, the spacing variable determines how big the sphere is going to be, the position determines where the sphere is going to emanate from, and then this one determines the collider that we're looking for based on the layer that that collider has. And the collider that I make for this is obstacle. And this is really cool because any object that we place into the world which is going to become an unwalkable node, so again like a building or a statue or anything like that, which if you place it into the world becomes unwalkable, that is going to be have this layer for obstacle. But even if we want other things which also, even if but it's okay because we can add other things as well. So if I thought of some other thing that I don't want to have on the obstacle layer, but I want it to be on some different layer, that's all right. I can give it water. So it will check for both of those, water, and it also check for obstacle. So we're kind of good to go in that sense. So that's what it does. So then if it checks this and it hits this thing, if it hits an obstacle, hits another tree, or it hits a rock, or hits a statue, or hits a building, then this will become false. But if it's not false, that's okay. That means we've hit nothing, so we can do this code again. And I believe the code is very much the same. Although, except for one difference, which I wonder why I didn't do. Okay, I know why I didn't do that here. Okay, so the only difference here is that I'm changing the scale of the rocks and the trees. The reason why I don't change the scale of the grass and the flowers is that because when you scale grass and flowers down, it looks really bad. It looks really obvious that you're dealing with a grid-based game. I'll quickly show you what I mean by that. So I'll set the grass to be a scale of like 0.3 and 0.3. And then I'll go into the grid script and I'll turn everything down to 0 and turn that down to 0 too. And let's make this 100% of the grid, so lots of grass. Now see how it looks really obvious that you're dealing with a grid. You can almost see the lines in between them. So that's why instead what I realized I had to do was that when I'm modeling these things, I had to make sure that they will slightly overlap. And I mean, it doesn't look great, but it looks better than it did before. It looks like it's exactly the same number of game objects, but it's not as clear that you're dealing with sort of this grid type thing. It just looks like a sort of sea of grass. So that's why I don't manipulate the scale with these variables. It only take up 1 unit. But I do it for these ones. So the way that you manipulate scale is here. So first I create this float called, the rotation stuff is all the same. But then I create this float, which is a random range between 0.5 and 1. Now remember that this will go up to, this is 1 exclusive, so it doesn't actually go, it will never actually go up to 1. It will go up to something like 0.998 or something like that. And then what I do is I use this method here, which is local scale. And if you set all of these axes to be the same value, then you're going to scale the entire object exactly across all dimensions. So if you have a tree here, and now it's on 1, if I just scale this one, and I just scale that one, it looks really awful. But then if I scale that as well, now it's exactly the same, but it's much smaller. So you have to make, if you want something to be exactly the same but smaller, you have to change all these variables equally. And that's what I did here. I have the scale value, which is a random range between 0.5 and 1, and then I give that same scale value to all the axes in the vector 3, and so this local scale variable makes it smaller or bigger globally, not just for one axis. Then I set the parent, and I do that same thing that I did before. This method is the method I use for instantiating rocks, but ultimately this is the approach I'm going to take for all of them. Some differences will still apply, so there'll still need to be 2 separate methods, but there won't be 3 separate methods. The reason being is that what we've done with these guys, if we've told them exactly the game object that we want at the beginning here. But this method allows us to determine the game object at every iteration of this for loop, which is really useful if you have lots of different types of rock. So if you have heaps of rocks and heaps of trees, heaps of different types of grass and flower, not just one type like this, then you want to be able to randomly select from those objects, from those game objects. So what I will definitely have to do is, instead of having everything in the same list, I'll have to, or the same array, I'll have to have one array for rocks, one array for flowers, one for grass, and one for trees. And then what we do, so that happens here. Much of this is the same, except here, where we make the game object. You see how in the next one we say the game object is this, the thing that we've put into the parameter there. We don't have any such parameter in this one. If you have a look, the only game object is the parent. There's no actual game object in the parameters, because what we do is we go through and what I'll have to, okay, so later on what I'm going to do is split these up into separate arrays. So I'll just quickly do that now. So what I did is I created some separate arrays for each type of object, and then I went here and I initialized them and I populated them. So these just have 1, but the rocks have 3. And then I had to change the parameters. I haven't done it for these ones yet, for grass and flower. For those ones, they have to be changed. But I'll show you how I change these, then you can change these yourself. What I did is I eliminated the need to have 2 separate methods, so 2 overloaded methods. I just have 1 now, which we just have these 2, as opposed to 3 like before. And this is responsible for both, this method does both trees and rocks. And what we do is that as a parameter, we add in the array that we want, and then we go into that array that we put into the parameter, and we go and go through that random range again. So in this case, for the case of the trees, you add the tree objects array, and then the index becomes 0 and 1, because there's only one object, so it's going to be 0 and 1 exclusive, so you just get that. For the rocks, we've got 3 objects, so we put in the rock objects, and then we go between 0 and 3. There is 3, so we start with 0, 1, 2, and then 3 is the exclusive final upper bound thing. And this works exactly as before, and it's much better. This is how I should have done it from the very beginning. To change these, you'll have to add the grass objects and the flower objects and have the upper bound thing as well. Very similar, basically identical to the trees. But you still have to keep these as separate methods, because these guys don't have any of that spacing stuff that these methods have to worry about, trees and rocks have to worry about. And as you can see, it's going to work exactly as before, but the code is a lot better, and it's easier to extend now and change and add more types of trees and stuff like that. Okay, well, I think I've talked about everything I wanted to talk about with this script. In the next video, I'm going to talk about Meshbaker. It's a paid asset, but when you see how amazing it is, you might be tempted to buy it. I certainly was when I found out. Okay guys, see you in the next video.